Good morning, everyone. In my last Physics 20 class, the students completed a lab activity in which they analyzed a ball bearing that was launched horizontally from a particular height above the floor, and they used the data to determine the experimental value for the acceleration due to gravity. The lab involved students collecting a total of 8 sets of data, and what they ended up having to do, which you should always do when you have multiple sets of data, is use each individual set of data and perform the calculation to determine, in this case, the acceleration due to gravity, and then repeat that set of calculations 8 times. It's really important when you analyze data in science that you don't average sets of data and do one calculation. That's just an incorrect analysis. If you have multiple sets of data, you have to do multiple sets of calculations and then average your final result. The purpose of this little video is to demonstrate to students and anybody else who's interested or can get some use out of it how you can use a Texas Instruments graphing calculator and input the data into your lists in the calculator, and instead of doing, in this case, say 8 sets of calculations, you can get the calculator to do one set of calculations with the entire lists and then get a new list with all of your results. I could just jump right into how to do that, but I think it's going to be useful if you see how a single set of calculations is done for one set of data, and I think it's going to be useful to understand the lab in order to understand that single set of calculations so you could use the lists in your calculator. So I'm going to go through a brief explanation of the lab here, and then I will go through one set of calculations without using lists and then use my calculator with the lists to complete all of the calculations. So what we did was we launched a small projectile. It was a metal sphere, probably about 3/4 of an inch in diameter, from the top of a balcony in a location in our building. And I had previously measured the height with which this ball bearing would leave the top as being 3.17 meters above the floor. And we measured 2 things. We measured the speed that the ball bearing left the balcony at, and we measured the horizontal distance. So here's the setup. I have a ramp that is basically just a V-shaped piece of metal that the ball bearing can be dropped on or from, and it rolls down the ramp, picking up speed, and it goes through the photo gate at the bottom of the ramp. There's a little photo gate here. You can see it on the right, and that's going to be telling us our speed in meters per second. On the floor, what I had was a land surveying tape measure that was marked off in decimal feet. And I had a group of students down there as well as a group at the top. And the group of students down there were keeping their eye on where the ball bearing landed so they could come to a consensus about what they believed the horizontal distance traveled by the ball is. So this is what it looks like from the side. And once again, this is 3.17 meters. If the ball bearing is dropped from that yellow highlighted dot at the top of the screen, then it's going to land a certain distance away from the balcony horizontally on the floor. If we were to drop it from a higher distance, then it would pick up more speed and the horizontal distance traveled by the bearing would be greater. So what the students did is they, at the top of the balcony, they maybe dropped the ball bearing from here, recorded the speed on the photo gate, and the students at the bottom recorded what they believe they could agree on for the horizontal distance. And then we just continued to move the ball bearing down to lower and lower heights to get lower and lower speeds and shorter horizontal distances. Students were then asked to explain how you could use the data to determine the acceleration due to gravity. With projectile motion, you always want to analyze horizontal motion independent of vertical motion. Although the horizontal motion happens at the same time as the vertical motion, what happens horizontally is not affected by what happens vertically, and the other way around is true as well. When you talk about the horizontal motion, it's uniform motion because there's no force pushing the ball to the right or to the left. Certainly friction with air at these low speeds with this shiny metal smooth ball bearing, friction with air is negligible. So the only quantities we can talk about for horizontal motion would be the speed horizontally, the distance horizontally, and the time it's in the air moving to the right. The speed, of course, is measured for each trial. It's measured by looking at the photo gate readout. And the distance is whatever the students agree to when they see where the ball bearing drops by looking at that surveying tape. The time is going to be calculated by using those two measured values for each trial. So if you take the horizontal distance traveled by the ball bearing in trial 1 and divide by the speed that it was moving at horizontally in trial 1, you'll get the time it was in the air in trial 1. When you look at the vertical motion, the only important players in this game, there's uniform acceleration vertically. The only important players are the initial vertical speed, the distance it travels vertically, the time it's in the air vertically, and of course the acceleration due to gravity, which is what we're trying to find. Just a note here, I don't have vector symbols above the VI, D, and the A because it's frankly unimportant. The ball is always traveling towards the floor, so there's no change in direction. I can get away with just using speed, distance, and magnitude of acceleration. VI is 0. Be very careful here. The speed that you record in the column on the left is the horizontal speed. And we've learned in class that a horizontally projected object initially is not moving up or down because it's projected horizontally. So its vertical velocity at that point is 0. It's going to travel 3.17 meters towards the floor for all trials. I had previously measured that. The time is going to be whatever time we have on the left-hand side of this chart. Because although it's traveling horizontally independent from its vertical motion, there really is only one ball bearing. It's doing two things at the same time. It's moving horizontally and vertically at the same time. And of course, the goal of the lab is to determine the acceleration due to gravity. You can use this basic kinematics formula. I'm not going to get into the explanation of the physics here. VI is 0, so that's what we can use to find the acceleration. If we rearrange it for the acceleration, we get 2 times d over t squared. So what you would have to do first is take your distance and your speed and divide distance by speed to get time. In your analysis next, what you would do is you would say, well, that's the same time on the right as it is on the left because it is only one object moving horizontally and vertically at the same time. Then you can take that time and put it along with the 3.17 meters into this formula at the bottom of the screen to get the acceleration due to gravity. So in terms of the analysis, the students had to show complete calculations for one set of data and show all their work. I'm not going to write that all down. I'm just going to do it on my calculator because that's not the point of the video. The point of the video is to get to the lists analysis. They then had to find the acceleration due to gravity using each of the remaining sets of data. So they would have to, whatever the set of calculations are they do in number 3 here, they have to repeat 7 more times. And then they have to find the average for all 8 of their accelerations due to gravity and calculate the percent error. So this is the data that they collected. You'll notice that the distances horizontally are measured in feet. So one of the things that students had to do was convert the feet to something that's more useful, like meters. You could, of course, use an app or an online tool to convert that, but I wanted them to understand what was going on, so I explained this to them based on my decades-old education. I said, I know there are 12 inches in a foot, so I'm going to multiply the number of feet by 12. I happen to know there are 2.54 centimeters per inch, so if I multiply the number of inches by 2.54, I get centimeters. Then, of course, you divide centimeters by 100 to get meters. So let's recap here. What they need to do is convert the feet to meters. Then they need to calculate the time using the horizontal distance in meters and the horizontal speed in meters per second, so they can use that time in the calculation on the bottom right of the screen along with the 3.17 meters to get an answer. So let's take a look at doing that for one set of data. I'm going to use the 4.19 meters per second and the 10.19 feet. And I'll just put up here the conversion method. So what you would do with this set of data is you would have to start by taking 10.9 feet, of course multiplying by 12 to get inches. This is how many inches that is. Multiplying by 2.54. This is how many centimeters it is. So this distance, when I divide that centimeter distance by 100, gives me 3.3 meters. That number that I've got right now, that 3.3 meters, is the horizontal distance when it's traveling with a horizontal speed of 4.19 meters per second. So for uniform motion, I take distance. I'm going to take this number, and I'm going to divide by the speed, which is 4.19 meters per second. This gives me the time the ball bearing is moving to the right, which of course is the same as the time the ball bearing is moving towards the floor. So now I can do the calculation on the bottom right of my screen, the acceleration due to gravity, and I'm focusing on the right-hand column here, is going to be 2 times 3.17, that's the vertical distance, divided by the time, which is this number, squared. And I get 10.08 meters per second squared, which is a very respectable number for high school physics. The acceleration due to gravity is 9.81 meters per second squared. Going a little bit off track here, if I subtract 9.81 from my experimental result, and I divide that by 9.81, and I multiply that by 100, this particular set of data is within about 2.8% error. That's incredibly good for a high school physics lab. I've always said for a very long time that if you can get anything within 10% error in a high school physics lab, you're doing things pretty good. Within 5%, you're doing an exceptional job. So this is a really well-designed lab, and the students did a great job collecting data. Now what the students have to do is perform that same set of calculations 7 more times. And that's not an epic journey. It's not going to take forever to do, but what I would like to do, and this is the focus, this is the pinnacle of this little video, is show you how we can enter this data into your lists, tell the calculator to do one set of calculations with the lists, and get the results. So the first thing you're going to do is you're going to grab your calculator. It's a Texas Instruments calculator that I'm familiar with, and you're going to find the stat key, which is, I guess it's 2 keys to the right of the alpha key. It's just up here where you can see my cursor, and go stat and choose edit. Now, what I'm looking at here are lists. Your calculator has by default 6 lists. If you use the right arrow to scroll to the right, you can see there are 6 lists, and then you hit the end of the line. If by chance you have some numbers in these lists already, it doesn't matter what the numbers are, but you go to your lists by going stat edit and you see numbers in there, you need to clear your lists by going to your memory management menu, which is down here. It's where you would go to reset your calculator. You go second, plus, but instead of resetting, you can reset your calculator. That will clear the list, but you don't need to. Option number 4 says clear all lists. It kicks you out into the home screen where you hit enter, and now when you go stat, edit, the lists are empty. What we're going to do is populate list 1 with the speeds. So I'm going to take a minute and do that. You can do the same, 4.19, 3.74, 3.25, 2.78, 2.79, 2.20, 1.41, and 1.68. Always check to make sure that you've entered the data correctly, because at some point we're going to quit out of here and we won't see those numbers anymore. I'm just double checking mine. It looks good. Now we're going to enter into list 2 the horizontal distances, and we're going to enter them in feet. I've got lines up here, and I hope you understand that this 4.19 meters per second is connected to the 10.9 feet. These are what we call in math ordered pairs. So I have to make sure that I enter them in the same order that they are in my table. So 10.9, 9.9. Take a minute and do that as well if you're following along on your calculator. And I'm going to double check not only the entries, but to make sure that they're lined up with the proper speeds. And it looks good. So I'm going to quit out of here. And what I'd like to do now is take a look at the set of calculations that we need to perform. The very first thing was we took our feet and converted them to meters. And we did that using, if you recall, 4.9. Well, I'm not going to use 4.9. I'm going to use all of those horizontal distances. Don't forget, I'm going to go stat edit again. My distances in feet are in L2. So what did we do with the horizontal distance? It's in red at the bottom of the left screen. We took the horizontal distance in feet, multiplied by 12, multiplied by 2.54, and divided by 100 to get meters. Now, if I hit my second key and the number 2, on my home screen, L2 pops up. And what I'm going to do is I'm going to multiply that by 12. I'm going to multiply it by 2.54. And I'm going to divide it by 100. Now, if I were to hit enter right now, it would pull the list up on my home screen and I could scroll through it, but I don't want you to hit enter and it has no value. I need to take this calculation that I've entered and store it somewhere else. And I'm going to store it as L3. My store key is right down here just above the on button. If I hit that key, I get a little arrow, and it's indicating that it's going to store this entire calculation wherever I tell it to. I'm going to go second L3, and now it generates all of these numbers, and if I scroll with my right key, are showing me the distances in meters now, not in feet. And if I were to go stat edit, I see there's a new list there, and it contains all of my meters. These feet are still in here, but I'm no longer going to need list 2. Let's quit out of here now. Now what is it we did? Well, we've calculated the distance in meters. Now we do the time calculation. We do this calculation. We took, I can't remember what it was, we took the horizontal distance of, I think, 3.3 meters and divided by the horizontal speed of 4.19. Well, let's do that with all of the horizontal distances and all of the horizontal speeds. So where are my horizontal distances? They're in L3. So second 3 gives me L3 divided by where are my horizontal speeds? They're in L1. L1. And I want to store this someplace because I'm going to use this in a calculation that's about to come up. Well, I have 6 lists, so why don't I store it as L4? I hit enter, and these are all of the times. These are all of the times for my different trials. And if I were to go stat edit and go over to L4, I can see them in there. So don't forget, L4 is the time for each of the 8 trials. So I'm going to take 2 multiplied by my vertical distance of 3.17 divided by my time, which is L4, squared. And if I want to see the numbers in my lists, I'm going to store that as something. I guess the next logical choice is L5. And this is generating now. What it's generated is all 8 of my experimental values for the acceleration due to gravity. If I were to go stat edit and scroll over to L5, I have them. Just as a bonus, you go stat, go over to the right to the calculate key, and you're going to do a 1 variable statistical analysis, but you need to tell it which list. And it's list 5. We want to average the data in list 5. Don't worry about the frequency of the list, just leave that blank and then calculate. The very first number that pops up in this cornucopia of information is your average. So your average acceleration due to gravity is 9.976, which has got to be less than a couple of % error just to finish this off. I'm curious, that's all. If I take 9.976, I think that's enough decimals for what we're talking about, subtracting the theoretical value of 9.81, dividing the result by 9.81, and multiplying by 100, it doesn't really get any better than that in high school physics. 1.69 or 1.7% error. Anyway, I hope you found the video helpful in terms of data analysis with your lists. Take care, everyone.